We are going backwards in the book a little bit at this point. We've covered everything in magnetism that I think we can really do in this format. And so we're going to hop back to where we were right when the school closed. We had been studying the basics of electric circuits. We looked at current and resistance, and we were about to get into more interesting circuit stuff. And so we're going to study a little bit of that in the remaining weeks that we have in the school year here. But it's been a while since we thought about most of that. So I have a recap screen up here to begin. We know that batteries are a source of energy. And specifically, you can measure a potential difference between the two ends of the battery. So if you just have a battery sitting there and you take a multimeter, you got to practice a little bit with some multimeters. If you take the two probes on the multimeter, put them on either end of the battery, measure a potential difference there. That's called the terminal voltage for the battery, because the ends are called the terminals. The word terminal means end. So batteries have that potential difference, which you can also think of as being an EMF. I learned the term EMF recently. But batteries provide that EMF or potential difference, and that can cause current to flow if you connect them to a complete circuit. You need a complete closed loop in order for any flow to occur. And there were two equations that we used to talk about resistance. First, when we defined resistance, it was in terms of this ratio here, R equals V over I. More commonly, that's rearranged in this order, V equals IR. Sometimes people call that equation Ohm's law, but it's not actually Ohm's law. There's this whole big thing about that. Technically, this is the definition of resistance, but if you call it Ohm's law, I'll still know what you mean, and I won't get mad at it. So in that equation, V is the potential difference that is being applied across some object. So like it could be a resistor or a light bulb or whatever, but it's the potential difference between the two ends of the object. I is the amount of current that flows through the object, and R is the resistance of that object. And if you're dealing with a simple object, like just a wire, then we can also write the resistance this way. And we did a lab on this where you measured the resistance of different lengths of this gray wire. And then I had a mystery wire in the lab that you had to calculate the length of based on its resistance. So in this formula, the first symbol is a lowercase rho, the Greek letter rho, looks like a curly P. And that represents the resistivity of the substance that the wire was made of. So if it's a copper wire, you would look up what is the resistivity of copper. Just like you could look up the density of copper. Doesn't matter what piece of copper you're talking about. Doesn't matter if you bought it at Walmart or you dug it up out of a copper mine in Africa. It's going to be the same number. All copper has the same density. All copper has the same resistivity also. The other letters in that formula are L for the length of the wire and A for the cross-sectional area of the wire. Most wires are round, so the cross-section is usually going to be a circle. So you would calculate that area by doing pi r squared. But in principle, you could have a wire with some other cross-section. It could be like a long rectangle or something like that. And then the other big formula that we made use of when we were looking at this stuff before was about power. The definition for power in an electrical circuit is P equals IV. But if the part of the circuit that you're looking at is made up entirely of resistors, then you can also substitute in the definition of resistance from higher up on the screen, And then you could rewrite the power equation in those other two forms that I have listed there. But I need to emphasize again that those other forms are only applicable to resistors. So you can't apply I squared R to a battery, for example, because a battery is an idealized object that doesn't have a resistance R. And if you even include a battery in the part of the circuit that you're looking at, it's still going to mess up the equation. So again, those last two forms are only good for resistors. Okay. So this is an idea that we saw before the school closed. We talked about it just a little bit. You put a bunch of resistors in a row, one after the other. That is referred to as a series of resistors. Just like the word series in other contexts always refers to things coming one after another. This is similar to just making a big long resistor, especially if these three resistors that I've drawn happen to be identical. It's really easy to imagine that this is basically just a resistor that's 3 times as long in this case. But even if they're not identical to each other, qualitatively speaking, it's like increasing the length. And as we saw on the previous slide, the length of a resistor is directly proportional to the resistance. So if you just make the resistor longer, or effectively make it longer, you're going to increase the total resistance. So if you have multiple resistors in series and you want to know what's the resistance of the whole thing, it's really easy. You just add together the individual resistances, and that gives you the equivalent or total resistance of the series. The other thing to keep in mind with a series combination, and this is again something that we saw little pieces of before the school closed, is that the same amount of current is going to flow through each object in the series. So again, my example diagram here just has 3 resistors all in a line. If 1 amp of current comes in on the left-hand side and passes through this resistor, there's nowhere for that flow of current to go other than to the next resistor. So all of that current has to go through this one, and then all of that current also has to go through this one, and all of that current is going to exit on the other end. So if things are in series, they will all have the same current as each other. Now they may not have the same potential difference. They could. If they're identical to each other, they'll end up having the same potential difference. But they don't have to. So imagine that there's a total of 12 volts between the 2 dots here. Let's call this positive 12 volts and call this one 0 volts, so the current flows to the right. If these 3 resistors are identical, then each one of them is going to have a potential difference of 4 volts. So if I'm at a potential of 12, I drop 4 by going through the resistor, which means the potential here is 8. Then when I go through the next resistor, I drop another 4, which means the potential here is 4. And then when I go through this one, I drop another 4, which gets me to a potential of 0. So again, if they are identical, you'll have the same potential difference for each one. But if they were not the same resistor, like say the first resistor is 10 times bigger than the other ones or something, you're going to get a different potential difference for different resistors in that case. They're still going to add up to 12, I said, if the total across the whole thing is 12. The individual potential differences will make 12 when you add them up. But the individual ones don't have to match. We'll see more about that in the next week's lesson. All right, so this is another way that you can combine objects in a circuit, and we did not really study this before we had to close down. This is called a parallel combination, because instead of putting them one after another, they're all side by side. So again, if you come in on the left, current flows until it reaches this intersection, but then it can split up. There are 3 different pathways provided. Those pathways have to recombine later, and then they go off. But unlike in the previous diagram, here the current, any given electron that you follow through the circuit, that electron is only going to go through one of these 3 resistors. It might go through the top, or it might go through the middle, or it might go through the bottom, but it's only going to go through one of them. Unlike in the series combination, where each electron that flows through has to go through all 3 of the resistors. So a parallel combination is about these alternate pathways. This is similar qualitatively to making the resistor wider. There's more space side to side. And if you think back to that formula from the first slide, the one that had cross-sectional area in it, area was in the denominator, because the wider the pathway gets, the easier it is to pass through it. So when you add parallel resistors, that's going to decrease the overall resistance of the circuit. And that can be counterintuitive, because you have this little brown object. It's called a resistor. It's literally the name, resistor. But what I'm telling you is that depending on how you connect it to the circuit, you can actually make the resistance drop. And again, that's because you're providing an alternate pathway or making the path wider. Similar to if you're trying to get down to lunch from 3rd floor in the upper school, the existence of that secret stairway makes things a lot easier because there's an alternate path that some of the students can take. If you remove that alternate path, the resistance to get from the 3rd floor to the cafeteria would be much greater, and the whole process would take a lot more time. So it's very similar to what's going on here in a parallel connection. So if you want to mathematically add together the effect of parallel resistors, it works out to be this weird thing with reciprocals. This is again related to the fact that the cross-sectional area was in the denominator of that resistance formula. And the book goes through the whole process of deriving this form. I don't want to talk through it. So it's not the kind of thing that you want to listen to someone talk about. If you're interested, you can find the derivation in the book. And the thing I want to emphasize about the formula here is that the left-hand side also has a reciprocal in it. So you have to take the reciprocal of each resistor, add those together, but after you've done the addition, you still have another step. You have to flip it over to take the reciprocal again in order to get the resistance. And lastly, in contrast to a series combination, in a combination like this, all 3 of the objects, or however many there are, I drew 3, they're all going to have the same potential difference, but they probably will not have the same amount of current. So if we think again about putting 12 volts between the 2 dots, the right-hand dot is at 0 volts, the left dot is at positive 12. That means that each one of these resistors, the top resistor, one end of it, is basically just connected to 12 volts. There's nothing in between the 12 volt location and the resistor. And the other end is connected to the ground at 0 volts. So the top resistor has a potential difference of 12. The middle resistor also has a potential difference of 12. And the bottom one also has a potential difference of 12. So if devices or objects are in parallel with each other, they all have the same potential difference. But again, in general, they're not going to have the same amount of current flowing through them. If they happen to be identical, then sure. Whatever current comes in, it's going to split equally, among the different pathways. But if the resistors aren't identical to each other, you're going to get different amounts of current depending on how easy it is to flow. If the top path is the easiest one for current to get through, because that has a low resistance, then more current is going to go that way. If the bottom is the hardest one, because it has a lot of resistance, then very little current will go that way. But again, they'll all have the same potential difference of different currents. So here's a summary of all of that. Series means there's just one path available, and there's multiple objects on that path. Parallel means that there's multiple paths available, and each one of those paths has only one object on it. So series looks kind of like this. Parallel looks kind of like this. This time I drew 2 instead of 3, but it can be any number. If things are in series, if resistors are in series, you can just simply add their R values together to get the total. If resistors are in parallel, you have to do this weird reciprocal thing instead. Objects in series will have the same current, but typically different voltages. Objects in parallel will typically have different currents, but will have the same voltages. Okay. Let's do a couple analyses here. I have a circuit with some parallel stuff going on and some series stuff, both in the same circuit, and I want to find the total or equivalent resistance of the circuit. So I've deliberately drawn this one in a way that kind of emphasizes the parallel part. The parallel part is right there. After current comes out of the battery, it goes through this resistor, but then it hits this intersection. There are 2 alternate paths, and they recombine here. So the 2 6 ohm resistors are in parallel. What I'm going to do is first figure out this section. So I know I can use the reciprocal addition formula. 1/6 plus 1/6 is 1/3. And then if I flip the whole thing over again, I get that the parallel section has a resistance of 3 ohms. So that means that I am effectively looking at this circuit instead. You can replace this parallel section with a 3 ohm resistor, and it won't change the behavior of the rest of the circuit. So if I've done that, I can now see that this 5 and this 3 are just in series with each other. There's nothing else going on, there's no intersections. They just come one after another. So that means the total resistance is 8. Let's try another one. So it's the exact same layout, all I did was change the numbers. So again, first I need to combine the 2 parallel resistors to figure out the resistance of that section. So 1 over R is 1 over 8 plus 1 over 24. That is not quite as easy to add as on the last one. So I'm going to rewrite it with a common denominator. I make them both over 24. Got 4 over 24. That would be 1 over 6. And then when I take the reciprocal, I get 6 ohms. So that means this circuit is equivalent to this, and 12 plus 6 is 18. So the total this time is 18. Okay. Change the layout. What we're looking at now, these 2 are in parallel with each other. And then these 2 are also in parallel with each other. But once I make those replacements, I'm going to have series resistors again. So those are the 2 sections I'm looking at. These are the setups to find the resistances of the 2 sections. Notice that now I'm writing with a -1 power on this side instead of having the 1 over r. Same thing. So 1 over 300 plus 1 over 150 to the -1. And then same thing with 1500 and 1000. Get some common denominators again. 3 over 300, that's the same as 1 over 100. So it turns into just 100. This one, the best common denominator is going to be 3000, so you get 5 over 3000. And then when you flip that, you get 600 ohms. So this is what I have simplified the circuit to look like. Battery, it's 100 ohm section, and then the 600 ohm section on the bottom. And that means the total resistance is 700. Okay. Question on this one is different. Instead of just asking for the resistance, it says what current is produced by the battery. So there is more than one way you could go about doing this, but I'm going to start by finding the total resistance again. I'm going to simplify the circuit. So from the battery, current flows up to this point, and then it branches off, and then it branches off again. So there are 3 resistors in parallel. There are 3 paths to get from this spot to this spot. I can take one of 3 separate paths. So that whole section is just 3 parallel resistors. So the resistance is going to be 1 over 12 plus 1 over 36 plus 1 over 18, all to the -1 power. The best common denominator here is going to be 36. 36 is 3 times 12. It's also 2 times 18. So I'll put all of them over 36. It's -6 over 36, the -1, which is 6. So again, that's not the answer. That only tells me that the circuit effectively looks like this. I could replace this whole thing with just a single 6 ohm resistor. Battery's 12 volts. I want to know the current. Current I is going to be 12 volts over 6 ohms. That's using the V equals IR formula. So it's 2 amps. Lastly, this is the same circuit. I've filled in the 2 amp answer from before. But now what it asks for is the currents through the individual resistors. Now again, it's not 2 amps. These resistors are in parallel, so they all have the same voltage V, which is 12. But they're not going to have the same amount of current. So the simplest way to go about answering this, given the information we have, is to make a separate V equals IR calculation for each resistor. So for example, the first resistor is 12 ohms. If I do V equals IR for that resistor, the potential difference across it is 12 volts. So if I divide the 12 volts by the 12 ohms, I get a current of 1 amp. For the middle resistor, again, the potential difference is 12 volts. V equals 12. Because this resistor, there's nothing between it and the battery on either end. So the potential difference is 12. Divide that by a resistance 36, you're going to get a 1/3 of an amp for the current. And similarly, on the 18 ohm resistor, go 12 over 18. That's going to result in 2/3 as the current. The thing that I want to point out about these answers is that if you add them up, 1 plus 1/3 plus 2/3. That's 2 amps. 2 amps is the current that we already knew was being produced by the battery. So what's going on here is that once the current reaches these intersections and splits up, the amount of current going down each of the 3 paths is still the same total amount of current. 1 amp goes this way, 1/3 of an amp goes this way, 2/3 of an amp go this way. But that's still the same 2 amps that came out of the battery. Now, we also could have found the 2 amps by doing the calculation from this slide first. Since I can tell from the diagram that each resistor has a potential difference of 12 volts, I could calculate each of their individual currents, and then I would know that the total current that comes out of the battery has to be the sum of those individual currents. So that's often going to be the case when you are analyzing a circuit, that there's more than one order you could go about determining some of the quantities. I asked the questions in a particular order this time, so it made sense to find the current of 2 first. But if it was a more free-form question where it just kind of said, like, figure everything out, then you've got options. You don't have to do things in any particular order a lot of the time. Now, there's one other thing that I want to show you. I realize this slide may look a little intimidating, but oops, my animations. There we go. Sorry about that. The schematic that you draw for a circuit can look a lot of different ways, even for a single design. So these top 3 designs, they are all the same circuit. I've kind of deformed them so that they don't look quite the same, but they are all the same circuit. All of them have, they have the battery, they have a single resistor, and they have a pair of parallel resistors. The parallel sections in series with the single resistor. It's kind of most obvious in the center diagram. There's this parallel section, and then a resistor after it. In the first diagram, I put the single resistor before the parallel part. It doesn't actually make any difference as far as the operation of the circuit goes. And in the third diagram, I've rearranged things even more. It almost looks like there's 3 parallel resistors here, but it's actually just these 2 that are parallel. You can tell because after you trace the path of the current, like at this intersection, there's only 2 ways that the current can go. It passes through this resistor, or it passes through this resistor, and then it recombines. After recombining, that's when the 3rd resistor comes up. Now the bottom row shows a different design, but these 3 are all the same as each other. This bottom design also has both parallel and series aspects to it, but I kind of inverted it. So there's 2 series resistors, and that pair is in parallel with this 1 resistor. I think the 3rd diagram is maybe the most obvious for showing that. So from the battery, I branch off to the upper path or the lower path. The upper path has 2 resistors in series, the lower path has just 1 resistor. But then the paths come back together and return to the battery. In the middle diagram, even though I put the battery in the middle, still showing the same relationship. Current splits 2 ways. One way has just 1 resistor, the other way has 2 resistors. So the last comment I want to make about this is that I'll talk about the center top diagram here. These 2 resistors are in parallel with each other. And this section, like the combination of them, is in series with the 3rd resistor. But it would not be correct to say that like this resistor is in series with this one. It's not. For two things to be in series, there has to be like no intersections between them, but there's definitely an intersection right here in between those two resistors. If you smush these together into just one part, that part is in series with the other resistor. But you could not describe either of these individual resistors as being in series with the third one. So anytime you're talking about series and parallel relationships, you've got to be careful about that kind of thing. Okay, that is it for this video. I also have a video of me playing around with the simulation, and also a link to the simulation to illustrate some of these same ideas.